These are the notes for LT5 in the Earth and Space Science unit. Target says you can use mathematical representations to predict the motion of orbiting objects in the solar system. There's a lot here. Okay, prior to this step, you should have been through the Solar System Explorer gizmo, where we noticed the elliptical orbits of Mercury, Mars, okay, all the planets within the solar system. We should have noticed the change in speeds of those planets. We should have a general idea of what an orbital radius is and an orbital period. So, as we go through here, make sure you've played around with that Solar System Explorer gizmo a little bit, because I'll be referring to it often. Keplers Laws. All right, there's 3 of them. The mathematical representation part does not come through until LT3. Not LT3, sorry about that. The 3rd law. So what you will need at that point, and you might just want to pause me and get it now, you'll need your formula sheet, because we're going to write out some steps on here, and hopefully you have a calculator available to you. All right, so you'll need those things eventually here within the notes. To start out with, I'm just going to give you the definitions on the left. So the first is also called the law of ellipses. Okay, so the law of ellipses, what we should know by now is that the orbit of a planet is an ellipse with the sun at one focus of that ellipse. All right, so hopefully, and if not prior to now you will know that an ellipse is a flattened circle. That is not a very good flattened circle. All right, so something like that. And let's say the Earth is right here in its orbit, and let's have the Earth over here at its orbit. We know the sun, and I'm going to exaggerate it. We are obviously not that elliptical in our orbit around the sun, but I'm going to exaggerate it to make it easy to see. So there's our sun. That would be one focal point, and there would be an imaginary one out in space somewhere around where I have that X drawn. So all of the planets in our solar system will orbit around those 2 focal points. All right, foci is the plural of those, if you ever see that word. Okay, from Solar System Explorer, hopefully we remember that all of the planets orbit in a counterclockwise direction. And the first law is just saying that that shape is an ellipse, and that the sun is one of the foci. All right, that's it for the first law. Very straightforward. Not so much with the second and third. So the second of Kepler's laws, also called the law of equal areas. This one is loaded. All right, and one of the first things hopefully we noticed in Solar System Explorer was that the planets in an elliptical orbit do not always travel the same speed. Okay, they do not. So as a planet approaches the sun, so as it's coming towards it, that planet's speed increases. Okay, and thinking about why, we've known since LT2, the inverse square law, the closer an object is, the closer 2 objects are, I should say, the stronger the force between them. So if the Earth is closer to the sun, there's a stronger force accelerating it towards it. All right, so as it comes near it, it's going to speed up right through here is where the Earth would be going the fastest. So the flip side of this is a planet, let's do it like this way, a planet's speed decreases as it moves away from the sun. All right, so the Earth, when it gets to this point, yeah, it's scooting, all right? But as its inertia carries it, right? So the gravitational attraction is still between the 2, but its inertia is swinging it around through here. It's going to be slowing down because gravity, the sun's gravity is almost like pulling it back, almost like the fish on the end of a fishing line. All right, it's trying to bring it back. And once it gets here and starts to bring it back up, it speeds up again. Okay, so that's a really important part of this, and you might be wondering, well, what does that have to do with equal areas? All right, this third bullet, just write it out, and I know this sounds strange, but don't think about it, okay, because it won't make any sense yet. So what we know is that planets sweep out equal areas in equal time intervals. Okay, planets sweep out equal areas in equal time intervals. Okay, now, bear with me. Think about some kind of round food, like a pie. Think about your favorite pie, a good old American apple pie, or your favorite kind of pizza. Right, maybe you got a favorite kind of pizza at Mitchell's, or I have a weakness for Jets pizza, but those are squares, so that's not going to work for this. It's got to be something round. And let's say that you've got somebody cutting this pie or this pizza, and they're not very good at having even slices. I would probably be that person, or I'm horrible at cutting these things. And so let's draw out, and it needs to be an oval shape, all right? So it needs to be elliptical. Somebody's going to serve you an elliptical pie. Maybe that's what you wanted for your birthday, was a pie instead of a cake. And think about what would happen here, all right? If we think about this in terms of an orbit, so there's our usual thing, and here's the Earth at the other location, all right? Let's say somebody's cutting out this pie for you, and they're not very good at it, so maybe it's Lentz doing this, and they cut you a long, skinny piece, all right? So a narrow, skinny piece of pie could easily have just as much good stuff in it as like a short, fat piece, right? So a real wide one, but short, okay, so not very long, kind of that tip, versus a long, skinny one, they would have the same amount of bites there. All right, so they might look different on your plate, but there's the same amount of stuff going into your body. That's what this is talking about, all right? So think about what we know from the first part of this law, and that is, I'm looking for a colored ink pen here, and I'm struggling to find one. We know from this first part of this law that the Earth is going fastest when it's close, all right? So this is going to be the fastest point. And the Earth is going slowest when it's the furthest away. So that says fastest, that says slowest. Let's say that we want to pay attention to how far this Earth travels in 100 days. Okay, so I don't know, just over 3 months. We want to see how far in the orbit on the orbital path would this Earth have went. Now, if we know the Earth is going faster here, I think most of us can easily understand then, well, if it's going fastest here, it would cover a greater space. So maybe it covered that much space there in 100 days. But over here, in 100 days, remember, that's the slowest point. So in 100 days, that Earth might only go that far. Okay, not very far at all. But to figure out the area, it's a triangle thing. And the triangle has to have its point at the sun, at one of the focus points. So it's like you would take this and connect it to the sun. It's okay if you don't have a highlighter, just shade it in. All right, so that would be, we're going to make this some lemon meringue or something, I don't know, something that color, I'm really stretching it. That would be what I mean by the short, fat piece of pie. So we covered a long distance on the actual orbit, but since the sun is relatively close, the area is just that space. Whereas over here, we didn't cover very far in the orbital path, but to get to the focus, to get back to the sun, we've really got to reach out. Now, you know my drawings aren't very good, but hopefully you can see what I'm talking about here, where even though we covered less distance, that area, because we have to connect it back to the focal point, back to the sun, that area is the same as that area. Right? That's what it means by it sweeps out equal areas and equal time intervals. So in 100 days, longer path in the orbit, but the sun isn't as far away. Shorter path in the orbit, but the sun's a long ways away. All right? And that's all because of this change in speed. All right, so that's the second law. Third law, this is where the math comes in. It is the law of harmonies. All right, the law of harmonies. And what that says, and this is going to sound very mathy, but just we'll break this down and it'll hopefully be pretty simple. Let's look at the symbol for period. Remember the T with the little things, little flaps there? That stands for orbital period. It's the time for one revolution. So for the Earth, that would be 1 year. All right, it's going to be in Earth years. So this is orbital period. When we talk about a radius, that's going to be the average distance to the sun. And that's going to be in astronomical units, which are AUs. The Earth to the sun, the average distance, we refer to it as 1, and then we compare everything to that. All right, so when you see that symbol, that's the period, that's the time around once, and this one is about how far are we from the sun, because we're never the exact same distance because we're elliptical, so it's the average distance. All right, so here's what it says. You can see it. The square of the orbital period. Okay, so that thing. That squared is proportional to, in fact, it's almost identical for a lot of planets. So it's proportional to the orbital radius cubed. We haven't done much with cubing in here. Okay, so the orbital radius is r. So it's saying they're proportional, which means r cubed is very close to equal to the period squared. Okay, so almost equivalent. Almost. Now, there's a gizmo that we do together in class. So if you're doing these, you probably missed the gizmo part too, where you have a chart. And I don't like the A. I'd rather they just keep it consistent and call that the radius. Where we have our planets, we have our radius, and we're looking for the period. All right? And so what I'm going to do is just make this right here, since you probably don't have that in front of you. So we're just going to call it planet radius in AUs. And you're going to be calculating the time around, the period, and that'll be in Earth years. All right? So I'm just going to pick a couple for this. We'll go Mercury, and then we're going to go one that's a long ways out, Neptune. All right, so Mercury and Neptune. Now what you really need to do is pause me if you don't have your formula sheet out and you have it available, because we're going to make this easier. This is the equation that's going to solve this. So this is technically Kepler's third law. I don't want to write on this one. Okay, so this is Kepler's third law. To solve it, we can ignore K. It's a constant. But when we discovered this law, when Johannes Kepler discovered the law, he set it so that K is 1, all right, in our solar system. And that's all we're going to deal with in this class. So we can ignore K. People struggle taking the cube root of stuff. So I've rearranged it for you. All right, I would write this on your formula sheet. And what it's saying is the orbital period is equal to the square root of the radius cubed. And I have this here because some people struggle a little bit with this. So the first thing you do is cube the radius and then take the square root of that to get your final answer, which is the orbital period. So that's the first step, is cubing the radius. And the second step is to take the square root of that. So here's how we do this. You'll be given the radius. You will always only solve for the orbital period. So Mercury is 0.39, and Neptune is farther out than us, so it is actually 30 times farther out, 30.06. Okay, so calculator time. First step, cube the radius. So we're going to go, let's turn her on, 0.39 caret 3. That means cubed. So we've been caret 2ing for a long time in here. Now we're going to caret 3 to get the cube. When you do that, you need this answer. And if you don't know how to recall this, that's a calculator skill you need in high school. So let's work on this. Because I catch a lot of people writing this down, clearing it out, and then going second square root and typing that whole thing in again. All right, that's silly. There's a lot easier ways. So I'm going to cube this again to get us back to that. 0.39 caret 3. Okay, so there it is. Now, to take the square root, it is second x squared. Okay, it is that square root. If, when you do this, you're using a square root that looks like this, with a little x in the corner, you will get the wrong answer. All right, that's waiting for you to say, like, to take the fourth root or the cube root of it, and we're not doing that. I don't even know if that's a word, the fourth root, but you know what I'm saying. It's waiting for you to tell you what x is. So you need to go second x squared to get this. That big answer is saved in your calculator right now. So to recall it, it's second, and then it's the secondary function of the answer key. The secondary functions of the negative key, technically, is where the ANS is. So second ANS gives you that. Then you hit enter, and now this is what you would type into Moodle for the answer. It's going to say round to the 10th. Since that is less than 5 there, your answer would be 0.2. Okay, so the period would be 0.2. So for the next one, for Neptune here, the farther we get out here, all right, so now we're at 30.06, 30 times farther than the Earth is. And we're going to cube it, caret 3. We're going to hit enter. We got that big old answer. Okay, now we need to take the square root of it. Second x squared, that's the square root. Second negative brings up the answer function, so it's recalling that big old answer. And we have 164.8. Okay, 164.8. So what we're seeing here is as that orbital radius gets bigger, that period is also getting bigger. All right, and we're seeing them go up at kind of an equal rate. All right, so there's a lot to this, obviously, okay, but that is how you calculate the period using Kepler's third law. Okay, it's how we can find it. And at this point, hopefully you've been able to go through Solar System Explorer, maybe Kepler's Law Gizmo, but we are all set. So good luck with LT5.